Welcome to our lecture 7, in which we are going to discuss basics of magneto-optical techniques. Again, magneto-optical business is a very big field, which is used, which probably worth also to have a separate lecture course. But here we will discuss only a basic and only the techniques which are the most commonly used in magnonics. So in particular, this will be magneto-optical Kerr effect, one of very powerful mechanism. So MOKE is used to study static magnetization distribution, but it also gives access to dynamic magnetization, so you can see propagating spin waves with it. And second, a powerful tool is Brillouin light scattering spectroscopy, BLS. And BLS has many advantages. Principally, it's probably the most powerful tool nowadays, which gives you all information about spin waves and intensively used in research. And then we'll speak a bit how to make BLS with time, waveverctor, and phase resolution. So, magneto-optical Kerr effect. Who knows Faraday effect? Optical Faraday? Andrii? What is this effect about?
It's about the turning of the polarization of the linearly polarized light while propagating through the magnetic material.
Great. So Andrii said that Faraday effect, it's when linearly polarized light, when it goes through a material with magnetization, it changes its polarization. Correct. Angle of polarization, or it changes ellipticity. Similar effect, but for historical reason, it's named another. Both were discovered in the 19th century, so as I remember, but this one later is a Kerr effect, and similar idea, but in this case we do not send signal through the sample, but we reflect it. Yeah. For magnonics, in reality, what does it mean? So there are Faraday filters, which are made out of yttrium iron garnet. So yttrium iron garnet is transparent, therefore you can study Faraday effect, you can send simpler through. And Kerr effect, if you work with permalloy, cobalt iron boron or so, then usually Kerr effect. But also from YIG there will be always something reflected from the surface. Therefore I assume for YIG also should be possible to do Kerr effect. And yeah, so idea is the same, but the difference is that we do not send samples through, a signal through, but we send our light and measure reflected light. So this is our sample, which has some magnetization M. We take linearly polarized signal. Who knows why S and P? S polarization and P polarization of light. Huh? No. Yeah, so it's from German language, then correct more or less perpendicular and parallel to the table, I think. And that's what we have. And then we send linearly polarized light. It means that we have only a vertical component, and then after it's reflected, we have two changes in effect. First of all, there will be change in the angle of polarization, and this is called Kerr rotation or Kerr angle, this theta s. But besides, there will be a ellipticity formed. So it means that we send nicely polarized, linearly polarized light, and we reflect, and it goes through elliptically polarized, which means that we have not only vertical but also a perpendicular component. So that's the main idea, how it works in practice. So if it's static MOKE, yes, then you just can see such a domain structure. For example, you have sample with magnetization. Here's magnetization up, here's magnetization down. Then you send polarized light, and you see that in scattered light, if my domain shown up, you will have polarization. So that's just approximately. In this direction, in reality, this effect is not so strong like in this graph. Usually change in polarization is quite small, but it's very easy to measure polarization and ellipticity. Nowadays, there are techniques which can measure very sensitively the change in polarization and ellipticity. But simplest idea is that we will have polarization here like that, and for the Because then we all discussed, main idea is that depending how your sample is magnetized, the reflected wave will have different polarization. And here is huge difference, yeah? These green arrows point in different directions. In reality, this change in polarization usually is miserable, I think less than 1 degree or so. But nowadays people can measure this ellipticity and angle very precisely, and then it works. So classification, here it's given it just as 3 different types, how you magnetize polar when you magnetize out of plane, longitudinal when you magnetize along, and transversal when you magnetize in plane but perpendicular. But this polarization-induced magnetization tensor here is different. Therefore, also doing it seriously, we need to keep in mind what kind of MOKE we are building and what we measure. That what we are building now in our group is M perpendicular, and later, if we will get money, we will install magnet for in-plane magnetization also. Good, so this is more description, not so suitable for MOKE, but for Faraday, that you can send always linearly polarized light can be split into 2 circularly polarized with opposite polarizations, and there will be a interference between, not interference, when they have, for example, group velocities are different, then always when you send input light linearly polarized, output light will be elliptically polarized at the output. Good, and I think we finished here that nowadays there are MOKEs commercially available when you see a picture with like a microscope, the whole picture is in, and you also can focus your light using such objective, and then you will have focus here in this point. And then you need to scan your sample, and in such a way you can have spatial resolution with resolution given by optical limitations of half of a wavelength, and you have temporal resolution. Good. So then now we continue with BLS. So the idea of BLS is a bit different. If in MOKE we were analyzing the polarization of the wave reflected from magnetic material in the presence of spin wave or without spin wave, yeah, so it measures also such a small change in the polarization given by the precession, magnetization precession. Here we measure something different. So in this case, we are speaking about non-elastic scattering of photons. So it means that we have an incident photon of frequency L stays for light, of wave vector K, L, which flies into our system, interacts with a magnon, which propagates in particles, so which has frequency, and U is written a wave vector of magnon, which is also a vector. And after the interaction, the new scattered photon will be generated. And here we have 2 options. So this is non-elastical scattering, which means that the scattering happens with a change in frequency. And like it's shown here, that new photon light frequency is given old photon light frequency plus minus frequency of magnon. And if your frequency decreases, that means that then we are speaking about Stokes part. And if your frequency increases of the light, it means that we are talking about anti-Stokes component. And it's all related. So these 2 mechanisms principally are different between, in one case, so if your energy became smaller, like in Stokes part of the new light, so it means that this energy went somewhere. And in this case, we speak about creation of a new photon. So it's a bit unusual. So maybe let's start with anti-Stokes. It's annihilation of photon. It means that your photon is coming with magnon and generating a new photon with larger energy. Namely that now this magnon disappears and we will get a new photon with larger energy. So this is annihilation of magnon. And here it's an opposite situation, that magnon and photon are coming, you will get new photon with smaller energy, and you can see it like 2 magnons will be at the end of the story. So there will be a burst of magnon. You take a bit of energy from photon and give it to a magnonic system. So therefore, be always aware that there are the stocks, anti-stocks models. So amplitude of stocks, anti-stocks is not always straightforward. Sometimes people speak about non-reciprocal behavior of spin waves. Sometimes it's a signature in which direction your wave propagates. It all depends on the experimental result, experimental setup, and on the sample and the investigation. Majority of the experiments, it simply ignore the amplitude, but sometimes people pay attention. Therefore, just keep in mind that there is something else going on. If you investigate some Zolensky-Maria interaction or so, some fancy physics and position of stocks and anti-stocks matters, you can define DMI. Yes, please.
When you the Stokes part, you take away energy from the photon, right? So how come the intensity is high?
Why intensity of this part is higher than this one?
Yes, when we take away energy from the photon. And so
Yeah, but its intensity, it's not about energy. Intensity, it's about number of magnons which are scattered. So it means you send many photons. Usually this experiment is performed in CV, continuous wave regime. So there is a laser of power, I don't know, 1 milliwatt or so reaching your sample. And it means, so it's kind of many photons, and only some of them are scattered on magnons. And then the more are scattered, the better. So actually here you see counts, less intensity counts. So it means that here 90 photons were scattered within some given time, which is a technical issue. And here it was like 15. And how many magnons photons are scattered on magnons, as I said, it depends on many other factors. Yes, please?
Are there cases where I only have Stokes or anti-Stokes part, or does always appear both?
Oh, I would be surprised. Never. So the question is if there is a case when we have only Stokes or only anti-Stokes. I have never met such a case in my career. I think in some cases when you will realize some unidirectional magnon transport and will play with energy momentum conservation, will do kind of not micro-focus. We'll discuss now when you analyze all K, but you will fix K. Probably you should be able to have such a situation that you will get at least one is strongly suppressed with respect to another. But I never thought in depth in this. Thank you. Good. So, what is going on there in physical principle? Just 2 quick slides. Here, very important is this literature. So this information was taken from the book Light Scattering in Solids, Volume 7. And in this case, there is a special section written by Burkhard Hillebrand from Kaiserslautern on Brillouin light scattering from layered magnetic structures. And in there, briefly is given this information, but also there are many references. So you can, if you want to go in depth, I recommend you to check this book and to go through the reference where all this was studied in details. But principally, for us, it's important that we are speaking now about electric field of photon. So it's field of high frequency, like 100 terahertz. And when this light is reflected from magnetic material, which has some magnetization M, there will be some electric polarization P will be developed. So what's staying in this case, E is just dielectric constant. It's a field of electric field. And K, it's a magneto-optical coefficient. So MS is clear, it's magnetization. So it means that we introduce here some parameter which we name simply magneto-optical coefficient, which shows us how strongly your light interacts with magnetic material. So if K is equal 0, there are such materials which don't care, but let's say weakly sensitive to the applied field, nothing changes. then K will be small, and correspondingly BLS response will be small. But in other cases, we need we are searching people usually for the materials with large magneto-optical coefficient. What we need to keep in mind that who knows which physical mechanism, fundamental physical mechanism, stays behind magneto-optical coefficient or magneto-optical interactions? Yes, spin-orbit torque interaction, spin-orbit interaction. You're right. Thank you, Andrii. Why it's important? Because spin-orbit interaction also is staying behind damping in spin waves. Because at the end of the day, when you excited magnetization precession, you have spin waves running in them, and they propagate, and you want to do some job with them, and so on. You want to keep damping as small as possible. But spin-orbit interaction at the end of the day is responsible for the transfer of energy from your magnetization precession into lattice to vibration. So it means that people are searching for magnonics materials with small spin-orbit interaction, like, for example, yttrium iron garnet. For magneto-optics, you need vice versa material with large spin-orbit interactions. Therefore, you always have to keep in mind that there is trade-off between damping and magneto-optics. If to speak about yttrium iron garnet, people learn to dope it with bismuth, which increases spin-orbit interaction and significantly increases spin-orbit interaction, and then damping, but damping also increases. Yeah, therefore you need just to be careful that with which materials you're working. Second point, that this magneto-optical interaction also depends on the wavelengths of your light. So, for example, Brillouin light scattering spectroscopy, which we will discuss here. I think classically they started with red light. Then people have found that green light is better, shorter wavelengths. And if to speak about yttrium iron garnet, we just asked our colleague Jaroslav Hammer in Prague, who performed Faraday measurements. And principally, he has shown that the shorter wavelengths, the better it is for magneto-optics coefficient in YIG. And that's why we moved our BLS has wavelength 460 nanometer. Also, usually green light is 532 nanometers. But again, here you need to keep in mind another issue, that when you have magneto-optical effect, it's one issue as a function of wavelength, but there is also absorption, so simple absorption. And it also increases for YIG. So the shorter wavelengths, the larger absorption. Absorption is bad. It means heating of sample. It means that not so many photons simply are going out. Therefore, you also need to get a trade-off between absorption and magneto-optics. So for nano-scale waveguide, nano-YIG, it really works better for blue light, for 60. But for thick YIG, probably still green could be a choice in many cases. Good. That's about the general story about the key. And now, that's how it's written in this book, how to solve this problem. So in general words, you need to split the problem into 3 steps. The distribution of the electromagnetic field inside the interaction volume should be calculated. Then second one, so that you simply know how your E profile looks inside of your media, magnetic media. So usually if it's YIG, it's epsilon 10. So it means that your laser still should have, so there will be reflection and refraction and so on. You need to take into account all this. The intrinsic cross-section problem is solved and electromagnetic scattered wave is determined. That's more or less part about interaction of photons with magnons inside of magnetic media, and the amplitude of the scatter wave outside of the sample is calculated. So then more or less you calculate what's going on with the wave outside. And so here is just a general statement that as soon as you have a magnon in your system, it introduces some fluctuation, fluctuating, or let's say alternative term, additional term to the polarization P, which we defined. We have this electric field with frequency E. So this I here is states for incident light or incident electromagnetic wave. Therefore, just this E here is oscillating, but not with frequency of magnet, but with frequency of light. Yeah, just one additional information. And then what happens? How to calculate scattering cross-section. So when you want to say how good your BLS is, if you see interaction, if you have scattered magnons or scattered photons with shifted frequency or not, then usually people refer to scattering cross-section, and you can get it from this value. So what is this omega capital here? So d omega capital is the number of photons scattered into solid angles as d omega. And we analyze these scattered photons in the frequency range from omega s to omega s plus d omega 10, d omega. And then this number of photons scattered inelastically in this angle and in this frequency range can be found by this vector, d2 psi over d omega s little. And principally, this is a very general definition of the scattering cross-section. What's important for us here is that there are two delta functions, which more or less gives us the information that we need to satisfy momentum conservation law and frequency conservation law. So energy and momentum should be always conserved. So here just mathematically plugged in into these delta functions, but at the end of the day, it gives us this with what I started. Yeah. So if you have energy of all quasi-particles you have in your system before some scattering and after some scattering should be conserved, the same should happen with momentum. So before and after scattering event, independently, if you annihilate or you give a burst to a magnon, please keep in mind that here we need to deal with vectors. Yes, so it's a sum of vectors should be equal to this vector. Good. Let us switch now to the technique. So how brilliant light scattering setup works. So here is a sketch. You see here a sample. The picture is taken from Burkhard Hillebrandt's all the presentations. So you have sample here, and you have magnetic fields as crosses. For example, in this case, it's pointing perpendicular to the plane. You need a laser, which works in continuous regime. Laser should be also very special. So usually in any laser there are wider, higher order harmonics next to main peak. And since you are usually working very close to your main peak, one should find a laser with high quality where the side harmonics are suppressed. Moreover, afterwards, pretty often here in addition, we put a additional filter, which filters out only main laser beam and suppresses additional as the side harmonics. So we send laser. Part of laser beam is already taken away with this beam splitter, and it goes to interferometer. From technical reason, just because it's a reference beam which is needed for interferometer to operate properly. The rest of light goes through. Then we can have here, for example, polarization, which is polarizer, which is needed mainly to change intensity of light. Since from laser it comes polarized light, then changing polarization, you can decrease power of your laser beam on the sample. It's important because when laser hits your samples, it creates a thermal pattern, and magnetization is strongly dependent on temperature. So it means that your laser will change properties of your sample, and therefore what you want to do, you want to decrease power as much as possible in order to have smallest influence of temperature on the light, on the sample. So we have a beam, then we reflect it, then we scattered, and here magnons interact with photons interact with magnons, and they fly back. you see that in this is one of the simplest devices concepts. Here there is a big lens is installed. Why? Because in order to follow energy and momentum conservation, particular momentum conservation, incident photons light is fixed. Here you can have different magnons with different K, which propagate in plane. For example, then there will be interaction between photons and magnons, and secondary photons will fly in different directions. Can fly in different directions. Therefore, you can either use it, you can analyze only one beam, one pass, I will show you later, and then you fix K of magnon, which is scatter. So you say that I want to see only magnons of the given K, because then it scatters photon only in one given direction. Or vice versa. You put big lens and you say that I want to kind of exclude momentum conservation from my setup. I want to focus only on energy conservation. Then I have big lens and I accumulate all photons scattered in all directions. That's what often is done. So then we have here another polarizer. Why? Because brilliant light scattering works. You can measure principally scattered from magnons, but also from photons. So there is big field of science where people measure photons in biology, for example, in medicine, to see vibrational modes and so on, using BLS phonons. Sorry, and light scattered by phonons do not change its polarization, as far as I know, but magnon does change polarization. So especially for at least for in-plane magnetized sample, when you have backward volume, a Diamond-Eschbach mode, the polarization from the thin films is changing polarization by 90 degrees. That's why principally in order to improve your sensitivity of your setup and so on, people put here simply polarizer 90 degrees to cut off unscattered light, because in your spectrum there is always light which was never scattered, because only very small fraction of photons are interacting with the magnetic media. And then of course you want to focus only on this scattered photons, and your polarization gives you additional degree of freedom, because you can suppress this part and you can see then better the side parts of your spectrum. Afterwards it goes through the Fabry-Perot interferometer. That's a main tool of the brilliant light scattering spectroscopy. We will discuss about it. This device is produced by John Sandercock, genius engineer in the Netherlands during his PhD time. And then at some point he started switched it to industrial products, or commercially started to sell these interferometers. In the world, I think everybody is using only his interferometers because there are no others. And at one point, as far as I told, that first interferometer he was building in his bathroom when he was, I think, PhD student or switched to postdoc. Yeah, and afterwards, more or less, when your laser, so this is a scanning interferometer, so it means that it changes frequency. It scans frequency, and at the end you have simply a single photon detector, so just photodiode, a semiconductor one, and you more or less count how many photons at which frequency is coming to you. And then analyzing these photons, you principally know all information about your magnons. Let's speak about a few words about the interferometer. Yes, please.
With the prism, I can only detect one frequency of photons at one time, right?
Yes, you can. So you can detect only one frequency at one moment of time. Yeah. Mm-hmm. That's how scanning. So it constantly changes the distance between the piezo in order to, between mirrors using piezo in order to scan frequency. Yeah. But we'll discuss it more. Good. What is Fabry-Perot interferometer? You probably remember from previous classes. So two surfaces which partially reflect your light. Partially it's reflected from the top surface, like it's shown here. Partially from the bottom surface, like it's shown here. And then these two light simply geometrically they pass different paths. So this one goes here, and this one goes, you measure from starting from this point, and they are parallel. So this delta S is important. So this difference in path, why it's important, because then these two laser beams, these two waves can be in phase or in anti-phase. In reality, you have not two but many, and therefore, depending which wavelength, which thickness, and which refractive index, you have either reflection or transmission, like it's shown here. And so how do you describe it? Yes, it's simple plane wave, E omega t k r. So you describe reflected wave amplitude as I plus 1, so kind of one next generation, as reflection coefficient times AI, so previous incident rate, and transmitted wave amplitude is given by d I plus 1, so any new iteration which is given by reflection coefficient previous one. So that's how it can be found. Delta S is given by the distance between mirrors, by the refractive index of your mirror, and by the angle alpha, incident light angle. Then the idea is clear that in some cases you have no reflection because they will be in antiphase, and means everything will go through the sample. In other cases, when these are in antiphase, they will compensate each other. It means that there will be reflection. Good. And now reflected signal will look like this. It's shown G, so simply defined by this phase accumulation, which is defined by delta S. And G here, this parameter is given simply due to reflection of your mirror for R1 minus R squared, and it means more or less coating of the surface, which can nowadays people can produce very good and tune it. Okay. Now, what we need to keep in mind is that if you plot here phase change, and here you will put a ratio of transmitted light divided by the incident light transmitted, you will see many such peaks. So it's clear that when you change wavelengths, for example, or you change the spacing between mirrors, you will have many resonances when you can send laser through, when laser light coming through. And then the problem in spectroscopy, which you want to do here with BLS, is how to get the absolute value. So you see some peak, but you don't know to which wavelength it corresponds, for example. And and here there is such a finesse of interferometer. Fabry-Perot interferometer, FPI, is defined, which is dependent on this delta mu, so kind of this shift in frequency of space here between two peaks. So, and this was exactly the problem which John Sandercock addressed, and he has found a great solution. So let us have a look. So what is the condition for construct interference for tandem Fabry-Perot interferometer? That half wavelengths should be given by d, which is a distance between the mirrors, divided by m, which is m is just integer. And we see here this tandem Fabry-Perot means that we have more than one interferometers. This is our first Fabry-Perot interferometer. This is the second one. And there are two ways how you can make mirror. You can make it like it's shown here, just standard mirror, where you have coating from both sides. But you can do it also differently. You put, this is a mirror with some transmission coefficient here, and this is another one, the same. And you simply mechanically keep a distance between these mirrors constant. The fun point that I think one of the largest challenges which he met when he developed the setup was vibrations. So it was necessary to find a way how to fight to overcome vibrations, and he developed these optical tables with active stability. when you more or less measure the vibration, and then with piezo you compensate them. And these optical tables are used nowadays not only for BLS but also for MFM and for many other devices. Good, coming back to the physics. This is the condition. If you want light to pass through both of your interferometers, it should be satisfied. And then at the end of the day, we are coming to such position, such formula that D1 over D2 is a distance between these two, ratio between these spacings, between mirrors in this and this interferometer, should be given by this ratio of two integer numbers. And that was very simple. He fixed these two mirrors. They are not moved. He wants to place this mirror on a scanning stage, and he can scan. So for different wavelength, for different distance, you have different frequency passing through, frequency of light. But second pair of mirror was placed with some angle alpha. And in such a way, he got a situation, so then you can rewrite it in this form. Such a way, if you have all these resonances for one interferometer, and you have all these resonances for another interferometer, because of this alpha angle, there will be shift only one of them, that one in the middle is overlap, and light easily passes through. But other resonances, there will be only some spurious small parts. And so in such a way, you got the possibility to scan, to more or less to get an absolute information, absolute value of your parameters of your photon which goes through. That's how this device looks like. So here is a pair of mirrors. So you see these are fixed. This all is sitting on a stage. Very complex device, a lot of optics inside, many new modulations. So this picture is taken from manual of John Sandercock 1993. And yeah, so that's how it looks like in reality. That's Chi Wang and Nura Tsenbach who are trying to align it when it moved to us from Kaiserslautern, where it was developed, the setup, to move to Vienna. And here you see the whole setup, how it looks like. So this big black box, it's your interferometer, which is the main part of the device. Here you see magnet in which we put sample. Here will be a little laser, semiconductor one, which sends light. Then it goes through objective, back, and interferometer, and many wires in order to control everything. Let us see what we can do with BLS. Or maybe there are questions too. Sounds good. As I said, main idea is very simple. You send photon, it interacts with magnon, and it carries principally all information about magnon. You need now to find a way to read out this information, and you need to know what kind of information you can read. In particular, we have microscopy. Micro means that you have spatial resolution. It's not spectroscopy, but microscopy, so there is this term. You can have time resolution, you can have waveverctor resolution, and you can have phase resolution. How to do, for example, a spatial resolution, like it's shown here. This is actually a real picture measured from macroscopic yttrium iron garnet with brilliant light scattering setup in the transmission mode. So you see here, we don't measure because you can send light from one side and measure with reflected light, but there is also old time approach when you take laser and you sample through YIG, and since it's transparent, and then you just analyze scattered magnons, scattered photons like this, and to realize scanning, it's very easy. So you usually never move light because it's very hard. If you move laser beam or you will move some lenses, then you might need to realign your interferometer, which is very tricky part. But what is easy to do is to move sample. Therefore, what we usually do, we just have some piezo materials. You have sample, you shine light, and then you just scan point by point. So it means you perform measurements in one point, you change, you perform measurements in another point, and so on. And then you will get such a 3D map or 2D map where you see intensity of spin waves as a function of a coordinate. In such a case, when you use just a simple lens to focus your light, you don't use objective. The spatial resolution can be, for example, 40 micron. So it's quite small resolution, but if your sample is millimeter by millimeter, then it's more than enough. It has time resolution of order of 1 nanosecond. We will speak a bit more. And also it has some dynamic range, more than 60 dB. It means that you can measure large signals with a BLS. What is more often used nowadays is so-called micro-focus brilliant light scattering. When you focus your light with micro objective, like it's shown here, then the same laser, again, some part of beam goes for a meter to keep it stable. Then another main part goes here to sample. Sample is sitting in the side of magnetic field. Photons are reflected, so here it's done in reflection mode. It means that all photons which interact with magnons are going back, accumulated by this objective, and go further with a change polarization. So here pretty often polarizing beam splitters, or if people want to measure both magnons and phonons, there are many experiments of this times, and vice versa. You remove beam polarization here, you want to have just beam splitter and then to see all scattered photons, and then you more or less analyze it again, bring it up to photodetector. What is important here is the objective, because this objective usually is with multiplication factor of 100, so, and it focuses, it sends light in a very broad cone of photons. So it means that here you have many incident photons in a very broad range of angles. Then these photons interact with your magnons and they fly back, and again you accumulate photons in some range. Therefore, there is some maximum K, largest wave number, which your brilliant light scattering spectroscopy can see, can detect. And but until this K maximum, you principally accumulate all photons, which which corresponds to some maximal K in magnons, and it's very cool technique, because then more or less you just focus on energy of this scattered light, and energy of your magnons, and you can say everything what you need about the structure. And here again, if you want to do spatial resolution, you just use piezo stage to move your sample. Yeah, so here is 2D scanning stage, and interferometer gives you, so what is the frequency range from half gigahertz? You cannot go below, because even in the best laser you have, there will be always this unscattered part of light, this middle part of spectrum, which is of order of, I don't know, 1-2 gigahertz wide. It means you cannot go to magnons with smaller frequency, but it's usually not needed. And the top frequency range of brilliant light scattering is principally 2 terahertz should be. But yeah, it's a question of scattering cross sections and so on. Usually people do not go above 100 gigahertz in their studies, maybe also because you need large field. And but up to 100 gigahertz or so it all works good. Spatial resolution of your of your BLS principally is given by distance between mirrors, because you can change it manually. If you need to increase the resolution, you just increase distance between lasers, but then you're getting problems that system is getting very sensitive to vibrations and to everything. So usually then it's harder to keep your system in the same state for if you need to measure a few days. Then it's getting a bit more complicated. But usually 50 megahertz resolution, which is very good, and which is important for the for our light for our field. But if you need real resolution like kilohertz, so then you need to stick to microwave technique, which we discussed last time. So antenna, spectrum analyzer, or any other technique. And finally, in microfocused, it means that in the previous case, in macrofocus BLS, you have very a large sample on millimeter scale. Micro-focused, usually a sample lateral sizes go from few microns down to 50 nanometers we measure nowadays. So principally to size of sample much smaller than spot, because you cannot focus, so your spatial resolution is given by the focus in spot, and this is given simply by optical limit, so half of your wavelength in the simplest case. Of course, when you measure, it's usually slightly bigger, but let's say 300 nanometer, it's a frequency resolution which you can have. But BLS allows you to have big laser spot and narrow waveguide, like 50 nanometer, which is spot is bigger than waveguide. Of course, signal drops down simply because volume where light interacts with magnetic material is getting smaller, but it still works. But in this case, it's very important that you need to know where you shine, because you can't see your sample anymore with eyes. And what people use, they use the same optical path, the same objective, but white light source, white or vice versa. For example, our BLS, it uses blue light, and in order to decrease noise level, we use here not white but amber, so kind of red light to shine sample. That then filter sustain and simply separate blue from shining light. And then you just shine this light laser onto the sample. It interacts, it scatters back, and it goes here. And then you have simple CCD camera where you see sample. In such a way, you can always, it's very important that you can find your sample. You can, usually then software is doing the job to scan and so on. You can, simpler than having a picture, everything works perfectly. You just more or less show the points, tell your system what it should measure, where to scan, and it all works good. Good, okay. Example, what can we see with BLS? This is, for example, some dispersion calculated analytically. We know already how to do it for for permalloy, nickel 81, iron 19, magnetized in this direction. The Maneshbach is the fastest mode if you want to work in micron range. This is micron range. And then you should keep in mind, we already discussed a lot, that there is first mode. If you have pinning, there will be second mode, there will be third mode, width modes. And important is that usually when you use such a uniform antenna, you can excite only odd modes, first, third, fifth, and so on. As then even modes like n equal 2 won't be measured, and won't be excited, because the same antenna field, which is uniform across the whole waveguide, will be trying to excite this and this part of the wave, which are in antiphase. Therefore, you will be trying to excite this one and suppressing this one in one moment of time, and after half period, you're trying to excite this one and suppress this one. Therefore, usually uniform antenna, you cannot get second mode. What do we see in experiment? In experiment, actually, we never see one mode. We see usually several. And if you will just take simple cosine function, like it's shown here, the simplest analytics, and you will plot intensity as a function of two coordinates x and y, and you will have some quantization over the width, w, and then what you do, you just take two different modes. When you have n, it's a first, n equal 1, and here n equals 3. When you will plug it in this formula, you will see this pattern. So wave kind of propagates in the form of, sometimes people say it's snake, sometimes people refer to like to autofocus, but that's not exactly the case. This is just interference of two modes, first one and third one. And then, for example, if Andrii would go to BLS and would plug such a sample into the his setup, if the width of waveguide would be a few microns, then he would immediately see this one pattern. And it's not very good, because it means that you always work with two wavelengths simultaneously. So if you want to have Magnonic crystal or filter, or you need to phase information something, you always have this pattern, which is problematic. Therefore, what Andrii does in his study, he just goes to the narrower waveguides when the frequency of third mode is shifted up. So in our case, for Itramar and Garnet, when you go below, let's say 300 nanometer wide waveguide, or so 500, we discussed it already in the when we discuss dispersions. Then this N3 mode simply has high frequency, and then you can have nice propagated spin wave where you will see just uniform, more or less exponential decay, but uniform distribution of the light. And light or intensity of scattered light. But coming back, so the best way is, let's say, because this beating between different modes is a problem for Magnonics. Therefore, try to always to think what to do and not be surprised. There are many papers. Vlad Dimido from Munster investigated that in details on macro scale, nano scale, micron scale. There are many review papers and so on. But if you will do now the same trick, but instead of n equal 1 and 2 equal 3, you put here 2, you will see that pattern is different. And this is a beating between first and second modes. Therefore, again, if you see something like that, you need to find out what's going on in my system, because I see odd or even a mode here. And this was shown by Peter Clausen and Kaiserslautern already some time ago. He did such a little trick. So that's his analytics, which I have shown. This is an experimental study. Okay, you can also find in literature more pronounced picture, which look exactly like this one, but that's something similar. But what you clearly see here is that when he made such permanent waveguide with such a bend, you see that you break symmetry here. It's not symmetrical anymore. Therefore, when spin wave propagates to this point and scatters, then, because now this field which is created here at the edges will work like re-emitting field for spin wave, you can describe it in such a way, and then you see that pattern became asymmetrical. So it means in such a way, simply by turning your waveguide a bit, it was a way how to excite a second width mode. And usually, he did it on purpose, but sometimes you really just want to do some majority gate or so, some device where you need to do many bendings, which is not uniform. And in this case, then we need to have a different, then we need to have more or less, if you see something like this, then you know that somewhere in your system something was not asymmetric and you excited even modes. So how do we, yes please?
Would it be possible to counteract the second mode if it just bends the other way? So it seems like the bend of the second one is always down, up, down. To bend your waveguide the other way, does it counteract?
So the question is, if it's possible to suppress excitation of this mode, if to bend it in the opposite way because it goes up and down. My guess would be no, because usually there will be, I don't know, some another component of magnetization or so. In reality, this any inhomogeneity will work as a source. So for this inhomogeneity, it's the same for the system in some way as if you would put not this antenna not through the whole width of the waveguide, but only localized it for the half waveguide, like it's shown here. Then what would happen? We would have this. You would excite second width mode independently and everything. So it won't help you to suppress it. Synthesizer, it's a device which sends you usually CV, a continuous wave microwave signal. So this is not light anymore. Now we are coming back to microwave business. We send 10 gigahertz, for example. And many experiments are performed in continuous wave regime, CV mode, when you just send the sample to your antenna, you excite constantly everything. Its static picture will be formed, and you just measure the static picture as long as you need in order to get all information you need. But if you want to have time resolution, usually you work with pulses. and microwave pulses. So there are two ways. So nowadays, all the synthesizers, or you can buy such a module that you have pulse modulation inside of your microwave source, and it will give you immediately microwave pulses. But what happens in reality, and that's what we did in the past, you put here such a RF switch, which is usually pin switch, pin states for p-doped intrinsic and n-doped semiconductors, so more or less diode. And that one is triggered by pulse generator. So you generate such pulses of usually TTL level, 5 volt, and duration, whatever you need, starting from 10 nanoseconds to 5 nanoseconds up to milliseconds. And rise and fall time of these devices, so good pin switches gives you 2.5 nanoseconds. So principally you can work with rather sharp, fast, short pulses. But when you then send it to your RF switch, what happens, you will create such a pulses. See that there are many pulses because usually you repeat the same experiment. In magnonics, especially in BLS, when through this pulse you can have only several scattered photons, and that means you need to repeat and repeat and repeat and accumulate it. Therefore, there is some repetition rate, which can be, for example, 1 microsecond, and you just do the same experiments, I don't know, billion times or so, and accumulate photons all the time. Yes, and depending what you need, if it's parametric pumping, so you can put here parametric some amplifier to get larger amplitude, but at the end of the day, the signal goes to your sample. So how time resolution is developed? So original old time resolution system, people used very slow photodiode, single photon detection with long so-called dead time. When it's after it obtains some photon, it needs a lot of time to recover because it should be single photon. It really should react on a single photon. Therefore, the resolution was done in the following way: that you send power. Yeah, you cannot do a time resolution for thermal magnets, for example, when you have no excitation. So you need always to couple to something. Therefore, at the end of the day, your BLS is coupled to this original signal, this one, and you measure starting from this point, like it's shown here, and then what was how the system worked, more or less. You know that you applied pulse and your interferometer is tuned to some frequency, and you're waiting until photon arrives, and then when photon arrives, your photodiode sends a signal. And you know when the signal arrived, but afterwards there was no more photons. So it means that per one pulse, more or less, you had always one photon. And this was always a question how it can be that you would imagine you have many photons, strong signal. It means that scattering would happen always at the beginning of the pulse, and then at the end you would simply have nothing because your diode is always off in that regime. And in reality, it's not the case. Even that approach worked very good because scattering efficiency is very small. So sometimes you have this pulse going through without scattering any photon, and therefore such rectangular pulses where you could see very nicely. How its modern BLS setups are working. So when photon is coming, what you send to your computer, more or less, some special card, you send two types of information. One is about arrival time, that you know when this photon arrived, and then after some shorter time, your diode is ready again to work, and you can it can detect more photons through one pulse. But second, what is going on when it sends you time, it also sends information coded in binary code about frequency, so at which point your interferometer was. And in such a way, you know both frequency and time resolution. Good. Yeah, it's pity, but I didn't show here some videos. But usually, Brillouin light scattering gives you at the end of a day, when you have spatial and time resolution, you can have nice animations, how your pulse is propagating, how it's excited, detected. Maybe next time I will show a few videos. And yeah, so you have more or less all information about your magnon, but you don't know its phase. Last time we discussed MOKE, and I said that Magneto-optical Kerr effect, it gives you phase resolution, because what you measure more or less this small magnetization component when you have precession, and when you have magnetization some given time in this direction or in this one, phase change will be, polarization change will be different. So MOKE is cool that it gives you phase resolution immediately. BLS doesn't give you phase resolution immediately. You need to do something with it. You need to build phase result setup. How do we do phase result setup? The easiest way to do it is to mix your optical signal with a reference signal. So here is just some sketch that if you have such a micron structure, you have antenna, you excite spin wave, it propagates, there is always a phase of difference of phase. And then if you will take some reference and of light scattered already by magnons, and will compare with the light scattered by magnons, then you will always have such situations that for this point, photons scattered from this point, when you mix it with reference signals, they will be in phase, and then you will see some maximum signal. And after half wavelength, there will be an out phase. Then you will see simply zero signal, destructive interference. So how does it work? It works the following. So here is a reference, and here is a sample signal. And if you have a situation like it's shown here in this animation. So you see now they are in anti-phase, and it means that we have white signal. So it means that signal scattered by light, by spin wave, and signal, your reference signal, are in anti-phase, you have white spot. Then if you change the position of where you scan, after some point you will reach the situation when your reference and scattered light will be in phase, so they will be blue. So we have it blue. It means that they are in phase. And in such a way, just then scanning your sample, you measure still only amplitude, but amplitude of two lasers together, mixed together. But then you will see such pattern, maximum, minimum, and this is your spin wave phase. So you can measure spin wave phase simply using additional reference signal, like it's shown here. There are different ways how people realize it, but the key trouble here is that the light which interacted with your spin waves and is here, it has different frequencies than incident light. Yeah, so you remember there was omega L, and at the output we have omega L plus or minus omega M. So there was a shift in frequency by a few gigahertz. And if you will send now, mix this shifted frequency with a reference of original frequency of light, you will see nothing. So it won't work. Therefore, what people do, they, first of all, you split here your laser. So this is your reference. You just take the same laser beam, you take part of energy of it, and send it up. And then you need somehow to change the frequency of your light. There were different ways, even using another spin wave waveguide here to induce this shifted frequency. But nowadays, people mainly use so-called electro-optical modulators. In the past, they were working only for fixed frequency. Nowadays, I think there are very cool devices which work with tunable frequency. And then you just need to trigger your electro-optical modulator with the same frequency as input antenna. So it means that there was microwave source at, let's say, 7 gigahertz, and the same microwave signal was used to excite spin waves at 7 gigahertz, and the same signal was given to electro-optical modulator. So what it does, it simply changes frequency of scattered light, at least part of that. So it means that here I have omega L, and here I will have again omega L plus minus this frequency of microwave. In addition, of course, people add here attenuator, a phase shifter, to make sure that you have proper amplitude of the wave. and that you can change with phase shifter. You can shift kind of your 0 point back and forth. Then some photons are interacting with magnons here. They propagate. Some are propagating here. You mix them up again to light, and then to interferometer you send mixture of two signals after interaction with spin waves and signal with which has been shifted in frequency by electro-optical modulator, and then at your detector you will see this pattern or phase pattern. Yeah, and here just some example for spin wave dispersion, for yttrium iron garnet, for different wave numbers. So you can fix frequency, but you change field applied, and then you can principally see you also change, sorry. You have, this is shown for two fields, 1821 Ørsted, 1831 Ørsted, and then by changing applied microwave frequency, you change wave number, simply following dispersion, which we discussed. And in such a way, then here you see measurements. So because this using this phase profile, you can get distance, so as it was shown here. This distance between two identical maxima, two identical minima, gives you wavelengths, and your wavelength gives you k, wave number, like it's shown here. And therefore, what you can do, you can just measure your dispersion curve directly, because you measure, frequency is given by your applied signal, or you can see it in your BLS, and wave number is given by that subtract simply from the phase result picture. So that's how phase resolution works. Another, again, just one practical advice, that's what I tried to do in this lecture course. Sometimes we have situations that you have end of sample, or in this case, it's yttrium iron garnet, this experiment, there was a gap, just mechanical gap, it was cut through. I don't remember, 50 micron wide spacing or so. And then you will see this picture without any phase resolution. So here there is no phase resolution, but you see maxima and minima. And this is because we obtained here simple standing wave. So you know that in standing wave, when it reflects from something, you just put these two cosine together, you do simple trigonometry, and you will get the one component which does not depend on time in standing wave profile. And it means that it is static in space. And that's exactly what you see here. So there will be a component, although wave it's running, kind of running and reflecting, but there will be maximas and minima, and from this distance you also can get your wavelengths. So principally, if you have no possibility to do BLS with phase resolution, but you need to know it for one particular point, principally you can think about standing wave experiment, and it will give you the resolution. The distance between these two maxima is half wavelengths in this case, like we know it from standing wave. And phase result measurements then would give you something different, because phase result measurements show you the real phase. Or for example, another way to get a standing wave would be, instead of just reflecting, to put two antennas, and then you will again you send the same microwave signal. There will be again such pattern. And in your amplitude, if you measure normalized amplitude as a function of coordinate, you see such a beatings. So they give you this information about the wavelengths. Of course, it's exponentially decays from sides, because here are antennas. Amplitude is the largest, in the middle is smallest. But if you will analyze phase with phase resolution, you will see such steps, such stairs. This is information about phase in this particular case. Other questions to phase resolution? A lot of information today. Yeah, but that's why we do it for YouTube, so that you will be able to see when you will have some concrete question. And that's what I show here. Of course, this is just basic overview. So I'm trying to give you such hints, which usually you have when you work already with this instrumentation, and maybe not necessarily easy to find in books. But if you need to go in depth, then of course you have to work with literature. Okay, I still have a bit of time. I would like to finish this lecture today, and I would like to speak about K-resolved BLS. So we know already how to resolve a place, so spatial resolution, how to get time, phase, and frequency. Frequency simply comes from the interferometer itself. Sometimes we want to know K, information about momentum of spin waves, but as I said, when you use objective and you use photons from all possible angles, you lose information about K because you collect also magnons from all possible angles. Therefore, there are special devices, special setups, K-resolved BLS setups, and I won't present you some, so for example, people simply put diagrams, like use big lens and put diagrams that they analyze only photons scattered in some given angle. That's kind of the first steps which were taken in BLS. But I will present you one of the latest setups developed by Dmytro Boschko, who is now professor at the University of Colorado, at Colorado Springs. And he developed the setup when he was PhD student in Brooker-Hillebrandt's groups in Kaiserslautern. And he had a separate problem. He was focused in his study on Bose-Einstein condensation of magnons. And usually magnons are condensating in this point here. So this is backward volume magnetostatic wave. You know already this dispersion. So here, because of dipole-dipole interaction, it goes down, and then due to exchange interaction, it goes up. And here we will get such a minimum of energy. And if you will inject enough magnons into your system, they all will condense here at this point of smallest energy. And you use BLS to see these magnons, and you have the same energy and momentum conservation, and everything is good. And your frequency resolution is fine, like it's shown here. But you see that when you resolve this frequency, you will see spectrum at the interferometer when this peak is large enough, high enough. It means you have many magnons and signal is strong. But you don't know which magnons are they. This can be this magnet, this can be this magnet, this can be this magnet. And therefore the question was that in addition to this setup, you need to introduce K resolution in order to get rid of this wave number uncertainty. Like it's shown here, that you know that I measure in this frequency range, but also in this K range. And then you can scan. How is it realized? Physically, idea is very simple. It's all common here. Here's written with this Q, these are wave numbers, and they are written in bold, so it means this is vectors. So what you need to do, you simply have to analyze the direction in which your scattered photon is flying. And if it's in that, and this direction gives you at the end of a day information about K of magnon. So simply analyzing direction of this photon, you know what was the K of magnon. And that's what is shown here. So what they did differently, introduced this idea together with Alexander Siriha in Kaiserslautern. They added metallic or dielectric mirror. Actually, with dielectric mirror works very good. They placed it under the sample, and then your scattering was going like this. So there was light coming into the YIG, yttrium garnet, this is from side. It was interacting with wavefront of the wave. It was coming down, it was scattered from the electric mirror, and then it was going back. And principally, then the question was to analyze the angle of the scattered, or not, the angle, what you change in the system is incident angle, the theta parallel. And then Q of spin waves can be found simply as 2Q of laser sinus theta parallel, like it's shown here in this case. A very simple formula. And simple formula, but means not very simple realization. So in some cases, classical K-resolved BLS, it's when you do nothing with light, you just focus it, put sand on the sample, and then you turn sample. And for different angle of sample, you see different momentum. What Dmytro has developed, he developed such setup when instead of turning sample, he turns a line beam with line laser beam, using all these prismas, and then in such a way he could scan all different key without moving sample. And the same setup allows you gives you a possibility principally to make K resolution, because now we kind of resolve only one projection of K, but you can turn sample, for example, and then you will get full information about K in parallel, K perpendicular. Recently, he visited our group and he has shown very nice dispersions for spin waves measured in full space. So there was Ky and Kx, and omega was measured by BLS. And I think I'm done for today. Other questions?
I have a stupid question.
Okay, please.
I've read somewhere about the BLS that from classical theory that can be just described as the correct reflection of the light on the moving grating of permittivity.
Yeah. So the question is that Andrii says that he read somewhere that you can describe Brillouin light scattering spectroscopy phenomena itself in a form of grating which moves with a certain speed. Yes, it's correct, and this is a bit more general. The fun point that all these wave scattering phenomena, they somehow similar, and they all about energy and momentum conservation. So all these phenomena like Bragg scattering, so when you have grating, you're right that your wave is forming okay, let's plot first wave, yeah? So this is a wave, and you can look on it like such a grating, and then if you will shine on this grating with light, then there will be Bragg scattering. So this is nothing else as a Bragg scattering, so it means that you will have scattering when this and this waves are in phase. Yeah? So it means that if this is A wavelengths, then if your how to say, okay, this is lambda light and this is lambda magnon, then you will get, if you send it in this direction, just simplest case, then you will have situations that when lambda L is equal to lambda magnon, you will have resonance reflection. And this is Bragg scattering mechanism, so we assume that it can be so that you see reflection from spin wave. Second question, what is going on with energy? If the system is static, it means that scattered light will have the same frequency. But your wave is moving, and if your wave is moving, it means that you need to take into account another physical phenomena, Doppler effect. So in principle, BLS you can say describe in terms of mixture of Bragg scattering and Doppler effect, because what happens in Doppler effect, if you have some frequency coming of omega 1 or incident, and you are reflected from object which is moving in the direction opposite to you, there will be reflection but with different frequency, omega reflected. If it's moving in this direction, which will be higher than omega incident. Yes, that's when we hear, when some car is coming, we hear that when it's approaching us, the sound is different when it's going away from us. And that's exactly what is going on. Therefore, here, but it gives you two conditions, and that's why important, that you, first of all, you need to satisfy energy conservation law. So a momentum conservation law, which is given more or less by Bragg scattering. And this guy tells you that you need to satisfy this, let's say, reflected is equal incident minus some delta F. And this delta F principle is given by the speed of your reflection object. And this gives you gives you possibility to satisfy a energy conservation. And in BLS, you remember, yes, that we need to So that's kind of, you can look on it like you said, but this comes from Bragg and this comes from Doppler effect. That's how I understand it. But all these phenomena are very close. So you just always need to, at the end of the day, it all comes to the energy and momentum conservation. Other more questions? If it's not the case, thank you for your attention.